All right, so we're very excited to have Sylvain Sorin giving the next talk. So stochastic games and moral are, interesting settings where a lot of perspectives are coming into play. We've seen a lot from machine learning and AI, but a lot of understanding of those games is founded on the mathematics of game theory. So Sylvain is an expert on this topic. So we're very excited to hear about his perspective on what's going on here. Thank you, Sylvain.
Many thanks. It's a great pleasure to be here. I feel a bit like a grandfather with all these young people, but it's very nice. New topic, new faces. I was there 40 years ago. There was a special year on game theory and mathematical economics at MSRI. And it's a completely new area now. And it's quite fascinating. Okay, so it will be very elementary, but it's a slightly different approach. I want especially to emphasize the interest of looking at continuous time for this kind of problems. Okay, so I will start by calling NoRegret procedure. So this is very, very elementary, as I told you, and it's just to fix notation. So we'll start with a finite, you have a finite set, K. This is a set of action. And then you have time, which is discrete. And at stage n, the agent will choose a component Kn in the set K. And then he learns this vector Un. Okay. And the outcome is the Kn component of the vector. And the regret is Un minus this component. Okay, so there is no assumption on the reward process, and the strategy of the agent is, as usual, a map from a previous history to mixed action. So this is called the external regret. Okay, so this is the choice of the agent. U is a vector, and this is. Okay, so the evaluation of the procedure generated by the strategy is a strategy will be basically a path here, okay, and used by the time in this set K. And the evaluation is the regret is the comparison of the payoff along this trajectory to the payoff on any constant trajectory. Okay, so you have a vector here, and you compare the average actual payoff to the average payoff that will be obtained by a constant component. So you want to generate a trajectory that will be better than all these constant trajectories. This is the notion of external regret, and we call strategy satisfies eternal consistency. So you see, this is game theoretical framework. I'm speaking about strategy and not algorithm if you have this property. Now, internal regret is more sophisticated. It's for every specific point here in this set, let's call it I, you look at the stages where you are using or predicting this component, and at these stages, you compare the, the outcome to any other fixed outcome. Okay? So what you generate here is not a vector, but a matrix. Okay, so this is the KL component of the matrix. It's 0 if you are not choosing K, and otherwise you compare K to L. You have the same notion of average regret. So it's comparison for each component of the average payoff obtained at the date you were using a specific choice. Everything is well known, and similarly, you define internal consistency. So the associated dynamics are, since you are looking at average, so you have a process Zn. Zn bar is the average, so it's defined by this procedure. So another way to write it is that the difference in the average process is 1 over n. This is the payoff at stage, or the outcome at stage n, and this is the average. Okay, so this is a discrete time random difference equation, and I will associate to this a continuous time deterministic differential inclusion. The way you do it is you replace the random variable by its conditional expectation. So this is un. You look at all the possible value of un that depends on the vector that you will observe. Okay, so this is the set Vn. Okay, so you write this like this. This is included is 1 over n because Vn is all the set of possible value of u. Okay, and this will be a noise because it's a random variable minus conditional expectations. And then we'll compare the trajectories of this average here to the trajectories induced by this differential inclusion, theta dot belongs to Vt minus theta t. Okay. So I think it's a nice place to recall Blackwell theorem. In fact, I met Blackwell, 40 years ago. We discussed a lot. It was I don't know if some of you met David Blackwell at some point. He was not only a genius, but he was really a very, very, very nice person. Okay, and so it's one of my best remembrance of Berkeley was this discussion with Blackwell. So Blackwell theorem is the following: you have a two-person game. You can assume finite action space just, and then the outcome is a vector in some Euclidean space Rk. Okay, and the game is repeated at each stage. You know the past history of moves. Okay, and as usual, the player can choose mixed action. Okay, so a strategy is as usual: play and use a sequence of outcome in Rk. You look at Z bar, which is the Cesaro mean. Okay, and what is interesting in this framework is whether you can approach a set. So a set C. So this is a set C. You are in Rk, and the play of the game generates a sequence of points Zn plus 1 in Rk. Okay, and you look at the average. So Zn bar stage. Okay, and you say that the set C is approachable by player 1 if there is a strategy of this guy such that this average will converge to this seat. Or you can say that the expectation of the distance will go to 0. It's excludable by a player if he can approach the complement of a neighborhood of this set. So the way you will use Blackwell theorem in our framework is to prove that if you look at the external regret, the average of the outcome will approach the negative Horton Rk, okay, meaning that all components will be negative. And in internal regret, you look at the matrix, so you want to approach this. Okay, so this is the use of approachability for NoRegret theory. Okay, so given X, which is a mixed strategy, a probability on this set, you define XA. So XA is the convex hull of the expectation induced by the strategy X. Okay, so it means that if player 1 play X, the expected outcome will be in this set. Okay, so there are 2 points in Blackwell theorem. One is the notion of B set and the sufficient condition for a set to be approachable. And the second is the specific class of convex set. So we say that the closed set C is a B set if for every point which is so for every Z here, you look at the closest point, let's say U in C, a closest point is C to Z. Okay, and what you want is that there is a move, a strategy of player 1, such that the set XA is on the other side of this hyperplane perpendicular to UC. Okay, so for every Z, you look at U, which is the closest point to Z in C, and you want that there exists X such that the set of expectation induced by this strategy lies on the other direction. Okay, so this is the notion of B set. Okay, so
quick question, sorry, is script P here, is this like Euclidean projection?
no, you don't need actually it's the closest, because you may have several points. Okay, you may have several points that are close. It's the closest point. Okay, yes. So this is this property. Okay, this angle is more than 80 degrees. Okay. And the Blackwell theorem says that if you have a B set, then it's approachable by this player just by using this strategy here. And this is the speed of convergence. So this is the expectation of the distance. And this is convergence in the probability. Okay. So the crucial property of the strategy is the control of the trajectory via this property. So this is the average at stage n. This is the closest point. This is the expectation of the next outcome. Okay, and this is this property here that you have angle. Okay. So in particular, you have come as a corollary that XA for any X is approachable by a player because he can generate a point here. So every half space containing this point has this property. So if you look at the draw, a necessary condition for a set to be approachable is that your opponent cannot approach the set with an empty intersection with it. Okay, so this is obviously a necessary condition for the set to be approachable. What is nice in the convex framework, it's a sufficient condition. Okay, and this is a consequence of the min-max theorem. So look, now you are in the convex framework, the set C is convex. Okay, and what you know is that for every Y of your opponent, the set AY, okay, will intersect the set C. Otherwise, the opponent could exclude the set. Okay, so now you take a point, you look at, so you take a point outside, you look at, here it's a projection, you look at the hyperplane. Okay, and what you know is that for every strategy of the opponent, the intersection with C will be non-empty. So if you look at the projection on this line, it means that for every strategy of the opponent, player one can get a payoff on this side. Okay, now you use the min-max theorem. Then there exists a strategy of player one that will force a payoff on this side. But it's a projection of what you can force in the game. So the XA has to be on this side of the hyperplane. Okay, so this is why in the convex framework, okay, either you have a B set or your opponent can exclude the set. Okay, so there are two components in Blackwell theorem. One is a sufficient condition for a set to be approachable, and the second is the analog of the min-max theorem for convex set. Dual version. So given a dynamics, the theta dot, so it's a first order dynamic and a set C, a sufficient condition for viability. So this goes back to Nagumo, a Japanese mathematician. This was done in 42, but it was not known because it was during the war. So it has been proved again by a lot of mathematicians, and it's a condition for viability. Viability means that the trajectory, if you start in C, will remain in C. Okay? And the condition is like this. The scalar product Pf, f is this function, has to be negative for what? For all P, which is the proximal normal to C. So what is the proximal normal to a set? You look at a set, okay? So you will see that the proximal normal, if you are at the interior, is reduced to 0. And otherwise, if you are at the boundary here, so you take a point theta on the boundary, and a proximal normal is a vector P, such that starting from theta, if you add P, then the circle or the disk center at theta plus P intersection with C is reduced to theta. Okay, so P is a set of direction such that the closest point from theta plus P to the set is theta. Okay, yes. this property of viability extends to differential inclusion, and you have this property. So if you have a differential inclusion, a condition for invariance, meaning that all solution of the differential inclusion will remain in the set, is this. Okay? And now I claim that this is exactly what we had here, because we mark that if you have a base set, it means that this is the property for every y, there is an x such that for every y, you have this property here. But you see, this was a projection from Z to U. Okay, so if you forget and you start from U, this is a vector P. Okay, so Blackwell strategy is starting from outside. You look at the closest point, and you want to be on this side. Okay, Nagumo theorem says this. The other say you are inside. You look at the point on the boundary. You look at the proximal map, and you want to stay here. Okay, so it's exactly the invariance condition for the differential inclusion, where V corresponds to the actual payoff at stage T, and theta was this. Okay, so this explains that Blackwell condition or Nagumo's condition or viability condition are the same. Okay, now how do you get approachability? It's starting from any point outside. You mimic the behavior if you were starting inside. Starting inside, you know that there is a strategy that will remain inside because you are viable. Okay, and then since both have the same V, the difference is you have theta 1 here, and the same V, so the difference will have exponential convergence. Okay, so the strategy theta 2, the trajectory theta 2 will remain in C, and the difference between the strategy theta 1, the trajectory theta 1 and theta 2 goes to 0. So this explains that you have approachability. Okay, so basically approachability and invariance appears as dual notion. Okay, the first corresponds to an exterior viewpoint. You are outside and you want to reach the state, and the second means that you are inside and you want to stay outside. Okay, and this is what I wanted to say concerning Blackwell. So let us prove convergence of the regret for using Blackwell theorem. Here we don't need all the strong form of approachability or B set, because the regret have a specific structure, okay? And also we want to approach not any set, not any convex set, but an orthant, which has a very, very specific structure. So there is two properties of the regret that will be used. For external regret, remember the regret is a random variable depending on your choice K. U is the vector you don't know. So assume that you take a mixed strategy, a probability on K, and you look at the expectation of the regret forever. You take the scalar product with X. Okay, this is always 0. Okay, it means that basically the distance to the mean in expectation is 0. Okay, so this is quite standard. And you have a similar property for internal regret. You have to be careful because internal regret is now in R. It's a matrix. Okay, so you cannot use directly a probability on K. So what you do is that when you have a matrix with non-negative coefficient, it defines a set of invariant measures, which are the probability on K satisfying this. Okay, this is basically if A is the Markov chain, these are the regular invariant measure. If you have a matrix with non-negative coefficient, it's the same proof, which is, by the way, a consequence of the min-max theorem. And then what you have is, remember, this is the matrix of internal regret. It's also a random variable. You choose K according to mu. Okay, you take the expectation of this matrix. You take the scalar product with A. This was the matrix you start with, and you get 0, which is a consequence of this. Okay, so these are the properties that we'll use to prove Blackwell theorem. Now, this was the part on the regret. Now, this is the part on the set. Remember that the set is an orthant. So I say that P is the potential for the orthant. It's a C1 function. It's 0 on the negative orthant. The gradient is always positive, and the scalar product is positive when I'm not at C. Okay. This was introduced, well, there are a lot of references I should have mentioned, okay? Regret starts with Annan and then with Blackwell. This notion of potential function for the orthant was introduced by Hart and Matt Collel. Okay? And now you have the proof of Blackwell theorem is quite simple. You take a potential, P, okay? And the P external regret based discrete procedure is just if the average regret is already in the orthant, you do whatever you want. Otherwise, you take a mixed strategy which is proportional to the gradient. Remember that the gradient has all component positive and is not zero, so this is well defined. The discrete dynamic is this. You look at the conditional expectation here. You forget about the average term. And the choice of sigma, remember the previous equality, x expectation with respect to x of the regret is zero. But x here is proportional to the gradient, so you have this property. Okay? So the continuous version of this can be written as this is W dot. The average value here of the expectation is a correspondence n of W, and here you have the term W. So the continuous version of this is this, okay? But now what I know about the values here, this is this property. The gradient time n is zero, okay? So as a consequence, you get that the potential P is a Lyapunov function associated to C. Why? But you look at here, you take the derivative, so you evaluate P on the trajectory. You have the gradient time W dot. W dot belongs to n of W minus W. This scalar product is zero. This was the previous, and this is negative. Okay, so you have this property. Okay, so this proves the convergence in continuous time. Okay, and now the convergence in discrete time follows for property of stochastic approximation. Okay, so the fact that you can replace the random variable by the conditional expectation, and that you have this property. What is nice here is that it's exactly the same proof for the internal regret. Okay, rather than taking the gradient, you look at an invariant measure for the gradient. You remember that the gradient is a positive matrix. You look at some invariant measure. You have this recursive formula for the internal regret matrix, the same property here. Now this is a product of matrices. Okay, so you have exactly the same property with the new potential. Okay, so this is the use of Blackwell theorem to prove the fact that the internal or external NoRegret vanishes. Okay, okay. So now remember that the total regret was this. This was a random variable. I will replace. This is the random variable corresponding to my choice. I replace it by the conditional expectation. Okay, and the difference is bounded martingale difference. I use Azuma's concentration inequality to reduce the analysis to this. Okay, so rather than looking at the random variable, I take here the conditional expectation. K are the extreme point I can replace by any point x, and then I get this notion of regret, which is the usual regret that you are working with, except that here it's on delta k, okay? But then you get rid of this, and more generally we have this approach, okay? So V is a norm vector space. I will always assume it's finite dimensional, and duality vector and duality map. So meaning that it's not necessarily a Euclidean framework. Okay, so I can have all this duality map here. And I will assume here X to be compact convex. In game, if you don't have compactness, then it's difficult to get equilibrium. So in continuous time, I will denote now by US the capital US the vector, and this is the regret, and the NoRegret property is like this. So we'll compare the performance of the algorithm in terms of regret, where there are three different assumptions. So general case, you don't make any assumption about this vector ut. Then what is called the closed form, ut is the function of what you are doing, okay? And the convex gradient is when ut is minus the gradient of a convex function. And then I will recall projected dynamics via Meyer descents and dual averaging. And first, a few remarks concerning the closed form and variational inequalities. So it means that here the vector u is actually a function of your choice. okay, for a continuous vector field defined on X. So it's especially interesting in the in the framework of games, okay. And so this was mentioned by Elad Hazan, okay. When you work in games, okay, the nice parameter is not the payoff function, it's the way you write equilibrium condition. And you want to write equilibrium condition as variational inequalities, and it's the function that appears in this variational inequality that will play the fundamental role in the learning process, okay? So you want to write well, you want that the equilibrium set is given by a set of this, okay? Where capital X is the set of strategy of player I, okay? So here, this is the relevant variable for player I. X is the n tuple of choice by all the players, and this is the choice of player I and an alternative choice. Okay? So the basic example where you have this is that obviously finite games. In finite games, phi I is just the vector payoff indexed by the move of the player. So you are given the strategy of the opponent, and you look at the collection of payoff induced by your own strategy. Okay, this is the vector payoff, okay, and Nash equilibrium. More interesting is continuous game with vector payoff. Okay, so you assume that it's C1 and concave with respect to your own variable, and then phi I is the gradient of your payoff with respect to your own variable. Okay. Yes. So to say that your payoff, okay, is greater than any alternative payoff if you change your strategy, since your function is concave and C1, can be written through a linear inequality on the gradient. Okay, and this is the crucial part. Okay, but now if you look at population game or wardrobe equilibria or mean field games, okay, X is the same place. So now a point here will correspond to a fraction of the population which is using each of the strategy. Okay, and then the vector field is simply the payoff function. So depending on the type of game, the right parameter that you use, okay, to describe Nash equilibria is not the same, okay? And this is this parameter that is the one that is important in the learning procedure. Okay? So for each player, the reference process is phi n of xt, which depend on the behavior of all players, but the trajectory of player I is not a function of the phi j of the other player. Okay, it's not a function of the evaluation of the other player. Okay, so well, this is clear that for each player you have the NoRegret condition, then obviously for the general process you have the same condition also. Okay. Now, the connection with variational inequalities. Okay. So this is the one I start with, and I will call it Nash equilibria for phi. Okay. And then there is a dual inequality where you replace here x by y. Okay. So it's what I call a set of external solution. Okay. The existence here of solution, if phi is continuous, is a consequence of Blackwell's theorem. This may have no solution, okay? But the set of solutions may be empty, but it's always convex. What is interesting is that if the vector field is dissipative, meaning that you have this property is anti-monotonic, okay, then we say that the game is dissipative, okay, and there is a theorem of Minty saying that in this case, the set SE is non-empty and set of Nash equilibria is included of this. Okay. And
what is the set S? I'm sorry.
It's the same that
The weak solution.
oh. Yeah. Okay. External solution. Okay, so if phi is continuous, okay, and you satisfy this, then you satisfy this. If phi is dissipative and you satisfy this, you satisfy that. Okay. Moreover, if phi is dissipative, the proof that this set is non-empty is a consequence of the min-max theorem. Okay. So in terms of complexity, it's very interesting. Okay. If you have a general continuous function, this may be empty, this is not empty. If phi has this monotonicity requirement, this is not empty. Okay? It's including this. Okay? And the fact that this is not empty can be proved using the min-max theorem. Okay? And this is basically what explains the result concerning the convergence of this algorithm. And the fundamental example of a dissipative vector field is a zero-sum game. So you have a function from the product space, and you look, so it's concave convex, and the vector field is the gradient with respect to the first component minus the gradient with respect to the second, and this is dissipative. Okay, so the basic example of a dissipative vector field is a zero-sum game. Okay, but you may have also. Okay, and now two property. Assume that you have a procedure that satisfies the NoRegret property. It means that this is a little O of t, okay, in continuous or discrete time. First of all, if the trajectory converges, then it will converge to an Nash equilibrium or to a solution of any. Okay, because you have this, this converges to phi of x, this converges to x, divided by t, this goes to 0. Okay, so then you take the average. All these terms converge to phi of t, so you have this. Okay, so this is negative. Okay? In particular, if you have a stationary point, then it's an equilibrium. On the other hand, if you look at time average trajectory, if phi is dissipative, the accumulation point of the average are in SE. And the point is that you use here the fact that it's monotonic to replace XS here. You see here, you cannot take any average. You don't have any linearity on phi. You don't know anything about phi. But you replace here by phi of y, and here this is linear. Okay, and this is the proof. Okay, so what you get here is that if you know that there are no regret algorithms, then you can prove directly that there are solutions to SE, because any accumulation point will be a solution. Okay, and this is one of the simplest proof of all this min-max theorem through NoRegret procedure. And in case of convex gradient, you use here Jensen inequality, but this is well known. Okay, so this was just last point, level function application. I'm looking at the continuous time formulation. I will say that a function with positive value is a level function if you have this property. Okay, so it depends on the ut and your trajectory xt. So it depends on the algorithm, and I want this property here: ut xt minus y greater than this. Okay? Now, if there is a level function, then the regret, which is the integral of this, is smaller than p of 0 minus p of t. P of t is positive, so it's bounded. So the rate of convergence of the regret is 1 over t. Okay? And if you are in the closed form and y star is in SE, then d of dt of py is given by this. Y star is in SE, so this quantity is negative. So it means that this is negative. This is a Lyapunov function. P of t of y star is decreasing. Okay? So this you can use for three dynamics. Projected dynamics, this is the projected gradient descent in discrete time. You look at the continuous time analogous, okay, which is given by this property here. So ut is the process that you will discover. Xt is the process that you generate, and this is the characterization. And the claim is that there is a level function, which is just the distance here. Okay, so you just look at the derivative here, and you have this property. So this implies first that the regret goes to 0 with the rate 1 over t. Two, that this is decreasing when you take a point x star, y star in SE. Okay, and this implies convergence of the trajectory using Opial's lemma. Okay, you know that this converges. Okay, and you know that the accumulation point of the average are in SE. So this implies that you have convergence of the trajectory. For mirror descent, you look at the continuous time version of mirror descent. So here you take a strictly convex C2 function. You look at the breakband distance associated to this function. And the mirror descent algorithm in discrete time is given by this. Okay? With this variational formulation, you go to the continuous time. You have this continuous time formulation. The previous case corresponds to 1/2 of the norm. And then you have a level function. So the breakband divergence associated to y and xt is a level function. So this implies immediately that you have convergence of the regret 1/T. Okay? And finally, for dual averaging, which is the continuous version of the Nesterov dual averaging, here you assume that H is bounded, strictly convex, where the domain is X. Okay? You look at the functional conjugate. This is in discrete time. Okay? Where you have a step size. The continuous time analogous is this. Xt is the gradient of the functional conjugate. Vt is the cumulative payoff. Okay? And then that you have that this Wt, which is h star of Vt plus h star. So it's a functional difference. Okay? As this property. Okay, dt of w is so it's a level function. Okay, so again you have this property of the regret. So you have analogous property in discrete time, and you have correction term, which is a function of the step size, and you have more regularity on the penalty function. You want the function not only to be strictly convex but strongly convex, but otherwise it's basically the same idea. I'm sorry I'm too late. I wanted to say something about correlation and potential game, but I will keep it for discussion. Sorry.
Thank you, Sylvain, for a very insightful talk. Unfortunately, my computer died of battery, so I didn't monitor the questions over there. The last thing I saw was Drew Funderburg, who was online, said that he had met Blackwell, and he was a very nice guy. And also he recommended him to go to the library and read a lot of novels. That's the last thing I saw on the chat. But are there any in the if you're on the Zoom call and you have a question, please speak up, because unfortunately I didn't see your question. Otherwise, I could start with questions in the room. Let me start with one that I have. So, Sylvain, you talked about dissipative games.
Yeah.
And just to connect a little bit, I mean, like to the also to like multi-agent reinforcement learning, and say, for example, you know, like two-player zero-sum, stochastic games. So these are not dissipative, but do you know, there is some recent work on games that are close to being dissipative, like, like dissipative up to some error and so on and so forth, where, like maybe not all no-regret learning algorithms converge, but like some, if you
okay, so two points here.
Yes.
One about stochastic games. So I'm very excited by all this work on stochastic game, but I have a question here. The question is that optimal strategy in stochastic game refer to some basically discounted stochastic game. Okay, it's not a one-stage game. Okay, so when you say that the strategy will converge to an optimal strategy, what is the meaning? Because you are not going to play the game once and again and again and again. Okay, so it's along the play of the game that the strategy will converge. But since the game is discounted, when the strategy will converge, the game is over.
Yeah, like stationary. So, let's say in stationary Markov policies.
Yes, very well. But so you use your stationary policy in the game. Okay, the game is discounted. If you are close to an optimal strategy after, let's say, 10,000 stages, the game is over essentially. Okay.
So the way people,
you're imagining repeating a stochastic game.
Yeah. So like you play a stochastic game until game is continued, and new round comes. So it's episodic. So
okay. So first of all, you have to truncate your stochastic game. Okay. So at some point, yes.
Sure.
Okay. So this is the and then but okay, fine. So.
Well, I mean, like, let's just view the stochastic game as a function, the pair function as a function of a pair of stationary Markov policies. You can look at the gradient, the policy gradient, the spectrum. It's not going to be dissipative. So, do you know positions under which it's going to be close to dissipative or like?
So this is the second point. I don't know. In fact, I don't know. The point is that when you are close to and you are not exactly, this may have a lot of consequences. Okay, and the typical example is you are close to a potential gain, but you are no longer a potential gain. Okay. In terms of dynamics, in terms of attractors, in terms of everything, you have a semi-continuity. So if you have an attractor, it will still be an attractor. Okay, but in terms of equilibria, it may be completely different. Okay, so the basic example of this is majority. You have 3 rooms, 2 rooms and 3 players. Okay, and you have one if you are the only one in your room, and otherwise you get 0. Okay, so you have 3 players. Okay, and here the 3 players in the same room, so this is not bad. The 3 players are in the same room. This is not bad, but otherwise you get this is okay. So this set here, which is homomorphic to a circle, is a set of Nash equilibria, where you put 2 players in a room and 1 in the other. Okay, and then if you are 2 in a room, you can go to the other room. Okay, you don't care. So this is why the set of Nash equilibria is homomorphic to the circle. Okay, and it's a potential gain. So there is another equilibria where everybody chooses at random, it's in the middle. Okay, and now if you have a potential gain, all these dynamics will increase the potential. Okay, so basically the attractor will be in the neighborhood of this set of equilibria. Yes? Okay. Now, if you have these 3 players, and rather than being indifferent of being with one of the other, they have preferences. One wants to be with 2, and 2 want to be with 3. Okay, all these Nash equilibria disappear because each time you put 2 persons in a room and 1 in the other, one of the 2 will prefer to be there, and the guy will turn. Okay, so whatever being the preference, it can be upside as okay. What you get is it's an epsilon potential gain. But this is no longer an equilibrium. Okay, the only equilibrium is here. But all the dynamics that are good for potential will still be approaching this set. Okay, and I think, and this goes back to the talk of Approachability last workshop. I don't know why, when you are looking at dynamics concerning behavior in games, it should converge to a point. There's no reason for me. It can oscillate. It will be stable. Here you have a good attractor, but it's not. So the set as a set is stable, but it's not a collection of stationary points. Okay. And so this is your question when you are close to.
Yeah, I guess
close to dissipative, it may be very, very different.
Yeah, I guess
okay?
What I was getting at is that I guess maybe that's for offline discussion, but like there are deviations from dissipativeness that can be exploited to create dynamics that actually do converge to equilibria. And if you care about equilibria, they give you a way to get there. Yeah, I guess the question of like, do we want equilibrium in the first place is a different question. So then a bigger question. So maybe let's continue that offline. If there are any other questions, please let me know. Or are there any in the chat?
No.
Okay. All right. All right. No, okay. Let's thank Sylvain again. Thank you, Sylvain.